Yeah, once again, good afternoon to the lecture 5 of hydraulics and hydraulic machinery. We are in the revision class of HHM subject dealing unit 5. The topic is hydraulic turbines. So in the previous class, we have discussed about the introductory classes of these hydraulic turbines. So in this class, we'll start about the concept of the various types of hydraulic turbines. That is the Kaplan turbine, the reaction turbine, and other draft tubes and other topics in this unit. Hope we'll continue the class now. So in the previous class, we are discussing about the problems related to the reaction turbine. We'll continue the problem. I think this is the third problem. So majority of the problems have been practiced in the classroom and you have already written some of the problems. So just refer your running notes. Just refer your running notes. So what are the problems you have practiced? And if you have any time, so you can practice the problems also, right? So apart from this, I will provide this PPT also in your group. So at the time of the before the exam, so you can open this PPT or PDF file, or you can read your running notes, those who have written the notes properly. Okay. So, but information is common to all the people. So, but for the problems, step by step చెప్పడం it is not correct in this revision class. So, I will just give the information బ్రీఫ్గా పైపైన చెప్పుకుంటూ వెళ్తాను. మీరు జస్ట్ రీకలెక్ట్ అంటే ఓహో ఇది కదా మనం చేసాము, సో ఇది ఇలా మనం చేసాము, ప్రాక్టీస్ చేసాము, ఇలా మనకి ఇన్ఫర్మేషన్ జరిగింది, ఇలా క్లాస్ జరిగింది, ఇలా ఇన్ఫర్మేషన్ పాస్ చేశారని మీరు జస్ట్ రీకలెక్ట్ చేసుకోండి ఇన్ దిస్ రివిజన్ క్లాస్, సో దట్ ఇట్ విల్ బీ సమ్వాట్ గుడ్ ఫర్ యువర్ ప్రాక్టీసింగ్. అంటే మేము ఆల్రెడీ మీకు రివిజన్ చెప్పాను అనుకోండి, మీకు కొంచెం ధైర్యం వస్తుంది చదవడానికి, రైట్? Now this is a question. Write the given data. Write the given data. Discharge width of the inlet head is equal to 150. Discharge at outlet. So these are the triangles for this reaction turbine. Pelton wheel వచ్చేసి మనకి W shape లో మీరు చెయ్యి ఇలా పెడతారు కదా, సో మీరు చెయ్యి ఇలా పెట్టినప్పుడు రెండు హ్యాండ్స్ సో ఎలా ఉంటుందో, that's why for this Pelton wheel you are having the inlet velocity is straight and outlet velocity is triangle. For this reaction turbines, because of the curvy nature of the vane, you are having both the triangles of the inlet and the outlet. Now, so based upon that, what is the initial velocity u1 pi dn by 60? As usual, you know that u2 is equal to pi dn by 60, and d2 is calling 36 meters per second. The discharge to the turbine is given by discharge q is equals to pi d dv. That is this one, the continuity equation. Therefore, Vf1 is equals to Q by area. This is the answer. Vf2 is equals to Q by area. This is the answer. Therefore, H minus V square by 2G is equals to Vw1 U1 by G. Here, Vw2 is equal to 0. Thereby, using the equation, we are getting V2 or Vf2 is equals to 2.31. Now, after substituting this one, we are getting the value Vw1 is equals to 56.1. Now the vane angle at the inlet and the outlet from the inlet velocity triangle tan theta is equals to 0.1064. Tan theta is equals to 0.1064. Now theta is equals to tan inverse of this one. Therefore, the theta value we are getting as 0.0643. Now taking the outlet velocity triangle, theta is equals to tan inverse of so and so. We are getting the value is 3 degrees 40.8 minutes. Now the velocity of the flow at the inlet and outlet Vf1 is equals to 3.183 and Vft is equals to 2.31. Now we are going into the next concept is Francis turbine. Francis turbine. The inward flow reaction turbine having a radial discharge at the outlet. Simple, the inward flow reaction having the radial discharge. Radial discharge ఎలా ఉంటుంది? The outlet to radial discharge, the discharge is radial. That type of turbines is known as Francis turbines, right? For the outlet, the type of discharge is radial. So that type of things are known as a Francis turbine. The water enters the runner and the turbine in the radial direction at the outlet and leaves in the axial direction at the inlet of the runner. Thus, the Francis turbine is a mixed flow turbine. So, ఏం చెప్తున్నాం final గా? So, if you get in any mid in your objective also, Francis turbine simply we are calling them as a mixed flow turbine అని చెప్తున్నాం. Why? Because you are having both the things, right? Axial ఉంది, radial ఉంది. Now, the velocity triangles for the inlet and the outlet of the Francis turbine are drawn the same way as in the case of inward flow reaction turbine. As in the case of inward radial flow turbine, the discharge of the Francis turbine is radial. At outlet, the velocity of the whirl WW2 will be 0. So, మనము ఇందాక మనం చెప్పుకున్నట్టు inward flow reaction turbine లో whatever the inlet triangle and outlet triangle are there, in the same way for this Francis turbine also, we are drawing the same inward flow inlet and the outlet triangles. Same inlet and outlet triangles, right? Next. Then the hydraulic efficiency of this Francis turbine is equals to VW1 U1 by GH. The important relations related to the Francis turbine are second in the derivation ఎందుకంటే it is same as that of the reaction turbine. The ratio of the width of the wheel to the diameter is given as is equals to B1 by D1. The value varies from 0.1 to 0.4. The flow ratio is given as this one, VF1 divided by root 2 GH. The speed ratio is U1 divided by root 2 GH. Now, take the first problem. The inlet outlet triangles, outer triangles same kabatti. The Francis turbine with the overall efficiency of 75 degrees, 75% is required to produce 148.25 kilonewton working under so and so. This is a peripheral velocity. The turbine efficiency is 22%. Now, what is defined? Determine the guide blade angle, the wheel vane, the diameter of the wheel, the width of the wheel. Therefore, what is the given data? The overall efficiency is equal to 75% at 0.75. H is equals to 7.62. The power produced is equal to 148. Now, what is the speed here? The speed is equal to 150 RPM. Now, the head loss is equals to 22% of energy. The discharge of the outlet is equals to radial discharge. Discharge ఎలా జరుగుతుంది? Radial గా జరుగుతుంది. Now, radial గా జరుగుతుంది కాబట్టి VW2 is equal to 0, VF2 is equals to V2. The hydraulic efficiency is equals to H minus 0.22 by H is equals to 0.78 మన క్వశ్చన్లో ఇచ్చాడు. Now, substituting this value, so we are getting VW1 is equals to, so cross చేసిన తర్వాత we are getting VW1 is equal to 18.34. For every figure, for every question, draw the figure as per the requirement. Now, what is the thing to find? The alpha, the blade angle and the inlet velocity. Therefore, tan alpha is equals to VF1 by VW1, that is equal to 0.64. Therefore, alpha is equals to 32 degrees, 37 minutes. Then the wheel angle at inlet, theta is equals to this one. Now, theta inverse is equals to, theta is equal to 37 degrees, 44.4 minutes. Now, the diameter of the wheel at the inlet D1, using this relation, U1 is equals to pi D1 by into N divided by 60. Therefore, you are getting the D is equals to so on. So, now the width of the wheel inlet. So, upon calculating this all the values, we are getting this one. So, the discharge Q is equals to, upon solving this one, we are getting this values. Finally, the B1 is 0.177. Right? Now, I will see some of the relations related to the Francis turbine. N is equals to B1 by D1. The flow ratio is given as flow ratio VF1 by 2 root 2 GH. So I think, okay. So this problem is, okay, this problem is repeated. No problem. దీనికన్నా ఇది కొంచెం నీట్గా ఉంది, మీరు ఒకసారి చెక్ చేసుకోండి. రైట్, దిస్ ఇస్ అ రిపీటెడ్ ప్రాబ్లమ్, బట్ దిస్ విల్ బి easy for your identification. Next, you see the Kaplan turbine. The Kaplan turbine runner is designed to develop so and so kilowatts shaft power. The net head is 5, the ratio is 2.9, and the ratio 0.68. The overall efficiency is 60%, and the diameter of the boss is 1/3 the diameter of the runner. Now write the given data: speed ratio, find U1, flow ratio, overall efficiency, right? The dB, diameter of the boss, and the relation using the shaft power by water power. You are getting this one. Now the discharge Q is equals to 227.27. By using the equation for discharge, keep on solving this one. D naught is equal to 6.788, right? By using the relation U2 is equals to pi D naught n by 60, n is equals to so on so 61.8. Therefore, ns is equals to 622 rpm. Now the next topic to be discussed is axial flow reaction turbine. By the name says that it is flowing axially. If the water flows parallel to the axis, if the water flows parallel to the axis of the rotation of the shaft, the turbine is known as axial flow reaction turbine. If the head at the inlet of the turbine is sum of the pressure energy plus kinetic energy, and during the flow of the water through the runner of the part, a pressure energy in the converted is converted into kinetic energy, the turbine is known as reaction turbine. For the axial flow reaction turbine, the shaft of the turbine is vertical. So ఈ కేసులో ఎలా ఉండాలి? axial flow reaction turbine లో the shaft should be vertical, just like a propeller, right? The shaft should be vertical. The shaft of the turbine is vertical. The lower end of the shaft is made longer, known as a hub. So the lower end ఎలా ఉండాలి? Just like a hub. This is a hub, just like a rotor, just like a bullet laga ఉంది, right? So just like it is known as a hub or boss. The vanes are fixed to the hub and acts as a runner to the axial flow reaction turbine. So ఎలా ఉంది దీనికి? ఈ హబ్ కి ఇది వచ్చేసి బ్లేడ్స్ అనేది these are fixed. The important types of axial flow reaction turbine are, so what are the various types of axial flow turbine? Propeller turbine and Kaplan turbine. సో ఇది మనకు చూడడానికి ప్రొపెల్లర్ లాగా ఉంది కాబట్టి దీనికి పేరు ఏం పెట్టారు? ప్రొపెల్లర్ టర్బైన్ అని పేరు పెట్టారు. ఓకే, నెక్స్ట్, when the vanes are fixed to the hub and they are not adjustable, the turbine is known as propeller turbine. So propeller turbine and then చెప్తున్నాం, whenever the vanes are fixed to the hub and they do not detachable or adjustable, that type of turbine we are calling them as a propeller turbine. Next, but if the vanes on the hub are adjustable, then the turbine is known as Kaplan turbine. Simple difference, right? Kaplan turbine ki propeller turbine with difference enti? So whenever the vanes or blades are adjusted, we are calling them as a Kaplan turbine. Whenever the blades or vanes are not adjusted, then we are calling them as a propeller turbine. This turbine is suitable where large quantity of water at low heads are available, right? Next, now see the propeller turbine guరించి అయిపోయింది. Now see the important parts of the Kaplan turbine: scroll casing, guide vane mechanism, hub, draft tube. ఈ ఫిగర్ ఆల్రెడీ మీరు క్లాస్ రూమ్లో వేసాం, నేను బోర్డు మీద వేసాను, మీరు ఆల్రెడీ ఫిగర్ రాసుకున్నారు. జస్ట్ ఇఫ్ యూ రీకలెక్ట్ ఇట్, మీకు కొంచెం ఐడియా వస్తుంది, రైట్? సో see here, the shaft is in this vertical direction, the movement is like this. Okay, so here the guiding vanes are moving, the guiding vanes are here. There is a water reservoir, the scroll casing, right? The guide vanes, the scroll casing, this is a tail race. So these are the main components of the Kaplan turbine. Between the guide vanes and the runner, between this guide vanes, the guide vanes and this runner, the water in the Kaplan turbine turns through the right angle into the axial angle direction and then passes through the runner. The runner of the Kaplan turbine has 4 to 6 or 8 in some cases blades and closely resembles a ship's propeller. It just resembles like a ship's propeller. The blades or vanes attached to the hub or bosses are so shaped that the water flow actually through the runner. Next. So దీనికి కూడా మన blades ఒకటే ఉంటుంది కాబట్టి, so the blades are normal just like your boomerang type. So that's why here also we are getting two triangles, one triangle at the inlet, other triangle at the outlet. Only for the case of Pelton మాత్రమే మనకి హారిజాంటల్ గా ఇన్లెట్ వస్తుంది, and coming to the outlet it is a triangle. So ఈ సోదంతా నేను చెప్పలేను, the theory, right? So just you read on your own, right? You read on your own. Now from this figure see here, ఇది మనకి 2 ఉందంటే అవుట్లెట్ అనుకుందాం, 1 అన్ని రాశారు కాబట్టి this is a inlet, this is a inlet, this is a outlet. Okay, so alpha u1 vw1 theta vf1 vf1, this is vr2 u2 pi vf2, like that. The discharge through the runner is obtained as q is equals to pi by 4 d naught square minus dp square into vf2. Therefore where d naught value tells to dv ante tells to vf2 ante tells. Then what is the important points of the Kaplan turbine? The important points are u1 is equal to u2, that is equal to pi dn by 60, where d naught is equals to outer diameter of the runner. Velocity of the flow at the inlet and outlet are equal. Therefore vf1 is equals to vf2. Then area of the inlet is equal to area of the outlet. Therefore pi by 4 into d naught square by minus dv square. Next, working proportions of the Kaplan turbine. So these are some of the formulas related to the Kaplan turbine. Now next concept to be discussed is draft tube. So draft tube, draft means the taper. The draft tube is a pipe gradually increasing the area which connects the outlet of the runner to the tail stress. It is used for discharging water from the exit of the turbine. So turbine nunchi water ni exit cheyadaniki the draft tube anedi manamu vadutunnamu. It is placed at the outlet of the runner near the tail stalk. Okay, this pipe is gradually increasing area called as a draft tube. One end of the draft tube is connected to the outlet of the runner and the other end is submerged below the level of the water in the tail race. The draft tube, in addition to save the passage for water discharge, has the following two purposes. But the first one, it permits the negative head to be established at the outlet of the runner and thereby increasing the net head on the turbine. The above turbine may be placed the turbine may be placed above the tail race without any loss of the net head, and hence turbine may be inspected properly. Next one, it converts a large portion of the kinetic energy, that is v square by 2g, rejected at the outlet of the turbine into the useful energy. Without the draft tube, the kinetic energy rejected at the turbine will go waste to the tail race. Therefore the draft tube, by using this draft tube, the net head of the turbine increases. So అందుకనే మనము draft tube అనేది యూజ్ చేస్తున్నాం. Turbine net increase అవడానికి we are using the draft tube for the tail race. The turbine develops more power and more efficiency of the turbine increase. ఎవరున్నారు గ్రూప్ లో? సో సేతస్వి ఒక్కటే కూర్చుంది క్లాస్ రూమ్ లో. Remaining people are sleeping, I think so. Okay. If the reaction turbine is not fitted with the draft tube, the pressure at the outlet of the runner will be equal to the atmospheric pressure. The water from the outlet of the runner will discharge freely into the tail race. The net head of the turbine will be less than that of the reaction turbine fitted to the draft tube. Therefore, without draft tube, the kinetic energy v square by 2g rejected at the outlet of the turbine will go water to the tail race. So just మీరు సెల్ఫ్ టాపిక్స్ ఇవన్నీ మీరు ఒకసారి థియరీ మీరు నీట్గా మెల్లిగా చదివారంటే మీకు అండర్స్టాండ్ అవుతుంది. సో ఐఎమ్ నాట్ ఇన్ ఎ హరీ, బట్ we have to take minimum 1 or 2, maximum 3 classes to complete a syllabus, to complete the unit. That's why I am reading very faster when compared to your normal classes, which are, that is your management science subject. అది మనం ఎంత డీటెయిల్గా డిస్కస్ చేసుకున్నాము. నేను ఇక్కడ చాలా ఫాస్ట్ ఫార్వర్డ్గా వెళ్తున్నాను, ఎందుకంటే మీరు ఆల్రెడీ అయిపోయిన టాపిక్స్ కాబట్టి మీరు జస్ట్ రీక్యాప్ చేసుకోవాలి కాబట్టి I'm doing like this. Then coming to the draft types of draft tubes, we're having a conical draft tube, simple elbow tubes, moody spreading tubes, elbow draft tubes. You see the figures of this one. Is a conical draft tube, simple elbow draft tube, it's a moody spreading tube. This is a draft tube with a circular inlet. So మీకు ఏమైనా క్వశ్చన్ వచ్చింది అనుకోండి పార్ట్ బిలో, సో వాట్ ఈస్ ద డ్రాఫ్ట్ ట్యూబ్ వాట్ ఆర్ డిస్క్రైబ్ ద టైప్స్ ఆఫ్ డ్రాఫ్ట్ ట్యూబ్స్ ఇన్ డీటెయిల్ ఆర్ అని వచ్చినప్పుడు మీరు దీని గురించి ఎక్స్ప్లెయిన్ చేయాలి. నెక్స్ట్, ద థియరీ ఆఫ్ ద డ్రాఫ్ట్ ట్యూబ్. Consider a conical draft tube, vertical height of the draft tube above the tail race. Y is equal to distance of the bottom of the draft tube from the tail race. Applying the Bernoulli's equation, section 1.1 and section 2. I think దీని గురించి కూడా మనం రన్నింగ్ నోట్స్ రాసుకున్నాం. సో ఐ థింక్ బాయ్స్లో ఫస్ట్ బెంచ్ వాళ్ళు ఒక థర్డ్ రోలో కొంతమంది రాసుకుంటారు రన్నింగ్ నోట్స్. గర్ల్స్లో వచ్చేసరికి ఐ థింక్ శ్వేత అండ్ సమ్ అదర్ 1 or 3 గర్ల్స్ హ్యావ్ రిటన్ రన్నింగ్ నోట్స్ క్లియర్లీ. మీరు ఒకసారి చెక్ చేసుకున్నారంటే దీని గురించి కూడా మనం ప్రాబ్లమ్స్ చేసుకున్నాం. ఐ థింక్, ఐ హోప్, రైట్? ప్రాబ్లమ్స్ చేసుకున్నాం కదా శ్వేతశ్రీ? ఎస్, రైట్. అప్లైయింగ్ ద బెర్నౌల్లీస్ ఈక్వేషన్. సో ఇక్కడ బెర్నౌల్లీస్ ఈక్వేషన్ సెక్షన్ 1.1 సెక్షన్ 2.2 అన్నప్పుడు సెక్షన్ 1.1లో ఏం జరుగుతుందంటే ప్రెషర్ ఎనర్జీ, కెనటిక్ ఎనర్జీ, డేటమ్, ప్రెషర్ ఎనర్జీ, కెనటిక్ ఎనర్జీ, డేటమ్ ప్లస్ హెడ్ లాస్ ఇలా ఉంటుంది. వేర్ హెచ్ఎఫ్ ఇస్ లాస్ ఆఫ్ ఎనర్జీ బిట్వీన్ సెక్షన్ 1.1 and 2.2. బట్ the pressure energy atmospheric pressure plus y is equals to PA by rho g plus y. Substituting the values in the equation 1. So we are, after deriving, we'll get in this equations. So finally, this will be the equation. Now, what is the efficiency of the draft tube? The efficiency of the draft tube is defined as the ratio of actual conversion of KE kinetic head into the pressure head divided by kinetic head at the inlet of the draft tube. Then what is the L? Let V1 is equal to velocity of the water at the inlet of the draft tube. V2 is the velocity of the water at the outlet of the draft tube. HF is equal to loss of the head in the draft tube. Therefore, the theoretical conversion of the kinetic head in the pressure head is draft tube is equal to V1 square by 2g minus V2 square by 2g. Therefore, the actual conversion of kinetic energy into pressure head is equal to V1 square by 2g minus V2 square by 2g minus HF. Now, the efficiency is given as V1 square by 2g minus V2 square by 2g minus HF divided by V1 square by 2g. ఇవన్నీ మీకు ఫ్లూయిడ్ మెకానిక్స్ సెకండ్ ఇయర్లో వచ్చి ఉంటుంది 2.1లో, రైట్? నౌ based upon this draft tube theory, we have derived some formulas. Based upon these formulas, మనకి ప్రాబ్లమ్స్ ఉన్నాయి. సో కమింగ్ టు ద ప్రాబ్లమ్స్, చదివే ఓపిక లేదు. మార్నింగ్ నుంచి I have took 4 classes. This is the 5th class. So these are the inputs. Okay, so for any subject till you complete your BTech, once again I am repeating you, read the question 2 or 3 times. మీరు ప్రాక్టీస్ చేయని క్వశ్చన్ కూడా, మీకు అంత సంబంధం లేని క్వశ్చన్ కూడా read the question 2 or 3 times. Write the given data clearly. దానికి ప్రాబ్లం ఉంటే మీకు వచ్చిన థాట్లో ఒక ఫిగర్ వేయండి, తర్వాత ఏం కనుక్కోవాలని రాయండి, టు ఫైండ్ ఆర్ టు డిటర్మైన్ అని చెప్పి రాయండి. తర్వాత ఇచ్చిన గివెన్ డేటా తీసుకొని బేసిక్ ఫార్ములా స్టార్ట్ చేయండి, రైట్ సమ్ క్యాలిక్యులేషన్స్ అండ్ లీవ్ ఇట్. ఆన్సర్ రాకపోయినా పర్లేదు, బట్ డోంట్ ట్రై టు ఎస్కేప్ ద ప్రాబ్లమాటిక్ క్వశ్చన్స్. ఓకే, వై? బికాస్ ప్రతిసారి చెప్తున్నాను, గివెన్ డేటాకి విల్ గెట్ మినిమం మార్క్స్ ఇన్ ద ఎక్స్టర్నల్, నాట్ ఇన్ ద ఇంటర్నల్. ఇంటర్నల్కి ఏదో ఒకటి వేసేస్తాము, బట్ కమింగ్ టు ద ఎక్స్టర్నల్ ఎవాల్యుయేషన్ జరుగుతుంది, ఇలా జరుగుతుంది. 2 marks, 1 mark for a question, 1 mark for the figure, 2 marks for the given data, 2 marks for the processing, 1 mark for definition, your formula, like this. Now, by seeing the question, write the given data clearly. Okay, the velocity, the discharge, the HF is negligible, like this. So figure veskondi, the draft tube, section 1.1, if section 2.2, this is a datum line anukunte, the draft tube is placed like this. The total length of the tube is 5 meters. Therefore, the The velocity at the inlet V1 is equals to discharge by area. Therefore, discharge is equals to 25 divided by pi by 4 d square, that is equal to 7.9 and 8 meters per second. Now, by taking the equation, Bernoulli's rho 1 by rho g, P1 by rho g is equal to PA by rho g minus HS. So on. So apply the values and substitute. Therefore, upon substituting, we are getting the HS value, y total length HS minus HS, that is a 1.1. Now the conical draft tube having the inlet and outer diameters 1 meters and 1.5 meter discharge water at the outlet velocity of 2.5 meters. The total length of the draft tube is 6 meters and 1.2 meters of the length of the draft tube is immersed in the water. ఎంతవరకు immerse అయింది? That is 1.2 meter of length of the draft tube is immersed in the water. అంటే ఇలా this way water, ఇది వాటర్ గ్రౌండ్ లెవెల్ అనుకుంటే లోపలికి ఎంత ఇమ్మర్స్ అయిందో క్వశ్చన్ లో ఇచ్చాడు 1.2 అని ఇచ్చాడు. Now, so these are the things. Then what is the find? To find the pressure head at the inlet and the efficiency of the draft tube. Now, write the given data: diameter of the inlet, diameter of the outlet, velocity of the outlet, total length of the tube in the water. Therefore, actual pressure head, loss of head, discharge through the tube, velocity at the inlet. Now, కనుక్కోమన్నాడు pressure head at the inlet. Pressure head at the inlet అన్నప్పుడు this is the pressure energy P1 by rho g. So P1 by rho g ఈ ఫార్ములా యూస్ చేసి now keep on doing the values and applying the values, you are getting 44.27 meters. Now what is the second thing you have to find? Efficiency of the draft tube. Therefore the efficiency is equals to, this is the formula. Now after substituting all the values here, after doing the problem, solving the problem, you are getting 76.3% of the draft tube efficiency. Now the next topic is specific speeds. A specific speed is defined as the speed of a turbine which is identical in the shape, geometrical dimensions, blade angles, gate opening, the actual dimensions, but the size of the that will be developed unit power when the working under the unit head, denoted by NS, specific head NS, right? Now the derivation of the specific speed, the overall efficiency of any turbine is shaft power by water power. The shaft power is equal to power developed by water power, that is equal to, keep it as 1. Now what is H here? H is equal to head, Q is equal to discharge, P is equal to power developed. Therefore from the equation 1, P is equals to inverse cross chain, we are getting this one. Now it is inversely proportional to the discharge into H, where again D is equal to diameter of the turbine. Now let us consider the diameter of the actual turbine, speed, tangential velocity, the specific speed, and the absolute velocity of the water. Therefore, upon solving this one, we are getting U is inversely proportional to the root H. The tangential velocity U is equals to pi dm by 60. Now applying 3, 4, we are getting this one. The discharge through the turbine is given as Q is equals to area into velocity. So that is this one, velocity, the discharge. So upon solving this one, right, the substituting value of Q in the equation 2, we get so on so value, P value, K value. ఇవన్నీ మనం చేసుకున్నాం క్లాస్లో, డీటెయిల్గా ఇవ్వలేదు, క్లారిటీగా చెప్పాను, రైట్? ద స్పెసిఫిక్ స్పీడ్ ఈజ్ ఈక్వల్ టు దిస్ వన్. నెక్స్ట్, based upon this we are having some problems to do. You are having 10 minutes to go. Now a turbine is to operate under a head of 25 meters, rpm 200, the discharge is 9, efficiency is 90, determine so on so head value, n value తెలుసు, q value చెప్పాడు, and efficiency is 9.9. the power developed and efficiency is equal to power developed by water power, this is the thing. Therefore P is equal to so on so, P is equals to this one. The specific speed of a machine ns is equals to n into root P h by h 5 by 4, this is equal to 159.6. Therefore power is equals to 1986. A turbine develops 9,000 kilowatts. So determine the specific speed. Specific speed formula. This is a specific speed formula. Now the power developed is 9,000. H is equal to 30. N is equal to 140. So applying these values directly, you are getting the answer. Here also, applying these values, you are getting the answer. Next, performance of the hydraulic turbines. So performance konukovalante, we have to find the behavior of the turbine. In order to predict the behavior of the turbine working under varying conditions of speed, high speed, output, gate opening, etc. The results are expressed in terms of quantities which may be obtained when the head on the turbine is reduced to unity. The three important unit quantities are unit speed, unit discharge, and unit power. And what's the meaning of unit speed? Unit speed is expressed in NU, where H is equal to head, U is equal to tangential velocity. So for that formula, U is equals to pi dn by 60. For given turbine, the diameter for the D is constant. Therefore, keep on solving, you are getting the speed. Next, coming to the unit discharge. How much amount of liquid is discharged per unit? It is defined as a discharge passing through the turbine, which is working under a unit head, that is 1 meter. Now let H is equal in the derivation same undavu exam ki. So to keep on solving this one, you are getting the formula this one. Next, for unit power, definitions unte you will get a definition like define unit speed, discharge, and unit power for a hydraulic turbines అన్నప్పుడు simple definitions మీరు రాయాలి. Now unit power formula, so finally what are the benefits of this unit quantities? If the turbine is working on a different loads, heads, behavior, therefore easily known for values of the unit quantities from the value of the unit speed under the discharge and the unit power. Therefore H1, H2, H3 are the heads under different turbines. N1, N2 are the speeds, Q1, Q2, Q3 are the discharge, P1, P2, P3 are the power. Using the equation 1, 2, 3, using the equation 1, 2, 3, 4, 1, 2, 3 respectively, we have drawn this one. Now, the characteristics of the hydraulic turbines. So the important parameters that are tested on this turbine are speed, power. Turbine గురించి మనం ఏ పారామీటర్స్ మనం టెస్ట్ చేస్తాం? We are having a speed, power, head, overall efficiency, discharge, and gate opening. The characteristic curves of hydraulic turbine are the curves with the help of which exact behavior and the performance of the turbine is to be known. So మనం centrifugal pumps లో కూడా in the last class లో మనము characteristic curves గురించి చెప్పుకున్నాం. There also we are seeing the behavior and performance of the centrifugal pumps or reciprocating pumps. In the same way, here also you are having the same characteristic curves with respect to the turbines. Then what are the various parameters which are varied during the test ante ivanni rayalannamata, right? The main characteristic curves, okay, the curves are called the characteristic curves. The following are the main types of the curves. First one is main characteristic curves, second one is operating curves, third one is Bushell or constant efficiency curves. Same curves names మనము యూనిట్ 6 లో డిస్కస్ చేసుకున్నాము. సో నేను ఎక్కువ చెప్పను దీని గురించి. యూ కెన్ రీడ్ ద ఓల్డ్ టాపిక్, ద centrifugal pumps లో ఏమన్నదో అదే మీ కెన్ డిస్కస్. See here the unit discharge ki, unit speed ki the variation, unit power ki, unit speed ki the variation. The main characteristic curves ఎలా ఉంటుంది, ఇలా ఉంటుంది. The main characteristic curves for a Pelton wheel, right? So ఇది omit చేయండి. These are the three main characteristic curves of a Pelton wheel. So if you get a question, what are the main parameters of this turbine లేదంటే కర్వ్స్ అన్నప్పుడు మెయిన్ క్యారెక్టరిస్టిక్ కర్వ్స్ అంటే మీరు రఫ్గా ఈ ఫిగర్స్ వేసి చూపించాలి. నెక్స్ట్ ఆపరేటింగ్ క్యారెక్టరిస్టిక్ కర్వ్స్. సో ఏం చెప్తున్నాం ఇక్కడ, ఇట్స్ ఎ గ్రాఫికల్ రిప్రజెంటేషన్ between the discharge as well as the efficiency on the power. So it is shown the discharge is a P and the efficiency is like this. You can omit it. Next coming is very important, governing of the turbines. So దీని గురించి కూడా నేను ఫిగర్ వేసి ఎక్స్ప్లెయిన్ చేశాను మీకు, రైట్? ఇంకేముంది చెప్పుకోవడానికి? I think the time is up. Selection of turbines. ఎలా చేస్తాం selection? Selection of a turbine, selection of a suitable type of turbine is usually governed by head and the specific speed, part loading operation. So selection of a turbine ఎలా చేస్తున్నాం? Head and specific speed, part load operation. Right? Head and specific speed, it is found that there is a range of head and specific speeds. Range అనేది ఉంటుంది అనమాట. Depends upon the meters. Less than 60 meters, 60 to 150, 150 to 300, 300 plus, 300 to 450, 450 plus, like this. So based upon the meters, head in meters, types of turbines are used. Less than 60 ఏం యూస్ చేస్తున్నాం? Kaplan or Kaplan turbine. ఈ రేంజ్ లో ఉంటే ఫ్రాన్సిస్ టర్బైన్, ఈ రేంజ్ లో ఉంటే పెల్టన్ టర్బైన్, ఈ రేంజ్ లో ఉంటే పెల్టన్ ఆర్ మల్టీజెట్. సో ద స్పెసిఫిక్ స్పీడ్స్ ఆర్ లైక్ దిస్. ద ఫార్ములా ఆల్రెడీ మీకు తెలుసు. ద క్యావిటేషన్, ద సేమ్ క్యావిటేషన్ మనం చెప్పుకున్నాం. ఏది? యూనిట్ 6 లో. యూనిట్ 5, యూనిట్ 6 లో characteristic curves, performance curves or characteristic curves, and cavitation. Both are same. The cavitation is defined as a phenomenon of formation of vapor bubbles of the flowing liquid in the region where the pressure of the liquid falls below the vapor pressure and the sudden collapsing of these vapor bubbles in the region of the high pressure. Same matter దీనిలో కూడా ఉంది. The precautions are also same. Precautions మీరు యూనిట్ 6 లో ఏం చదువుకున్నారో దీనిలో కూడా అదే చదువుకోండి. Effects of the cavitation. So these are the effects. Same thing. Surge tank. I think the surge tank గురించి కూడా నేను ఫిగర్ లో వేసాను. So these are the very important definitions to be highlighted at the end of the each unit. So hydraulic machine అంటే ఏంటి? Then what is the gross head? What is the total head? Okay. The efficiencies ఏమేమి ఉన్నాయి? 4 efficiencies ఉన్నాయి. Mechanic, hydraulic, mechanical, volumetric and overall. So fourth one కూడా ఉంది. You can write fourth one as a volumetric efficiency. Then hydraulic efficiency అనేది is a formula. Okay. సో అన్నిటి గురించి నేను లాస్ట్ లో మీకు ఫార్ములా స్పేస్ చూపిస్తున్నాను. సో డోంట్ గెట్ వరీ. రైట్? Just read this point so that you can easily understand. The discharge of through the turbine is given by the Pelton wheel కి వచ్చేసి ఇది, ఫ్రాన్సిస్ టర్బైన్ కి వచ్చేసి ఫార్ములా, కాప్లన్ టర్బైన్ కి వచ్చేసి this formula. Draft tube అంటే ఏంటి? It is generally used for increasing the area used for discharging the water from the exit of the reaction turbine. Right? So this is a formula for this draft tube. Yes, draft tube formula. Okay. The specific speeds formula వచ్చేసి is defined as so specific speed formula. ఇవన్నీ మీరు మీకు ప్రాక్టీస్ కోసము ప్రాబ్లమ్స్ ప్రాక్టీస్ చేసుకోవడానికి మీకు హైలైట్స్ లాగా చూపిస్తున్నాను. The unit quantities, so the important characteristics, main operating and molecular constant velocity, governing of this also. Then what are the important questions అంటే ఎలా వస్తాయి? Define the terms hydraulic machine or turbines or pumps. Differentiate between the term and the pumps. What do you mean by gross head, net head and efficiency of the turbine? Explain different types of efficiency of the turbine. Then explain clearly the terms used in the Pelton wheel. Gross head అంటే ఏంటి, net head అంటే ఏంటి? How do you classify the turbines? Then differentiate between the impulse turbine and reaction turbine. మీకు డిఫరెన్షియేషన్ కూడా మీకు నోట్స్ చెప్పాను, మీరు ఆల్రెడీ రాసుకున్నారు. Differences between impulse turbine and reaction turbine, differences between radial turbine and axial flow turbine. Inward and outward అంటే ఏంటి? Kaplan and propeller turbines. సో ఇంత డెరివేషన్స్ రావు, వస్తే నేను చేసేది ఏం లేదు. వాట్ ఇస్ ద బేసిస్ ఆఫ్ సెలెక్షన్ ఆఫ్ టర్బైన్ ఇన్ పర్టికులర్ ప్లేస్? What are the unit quantities? Define the unit quantities. Derive the expression of unit speed, unit discharge and unit power. Characteristic curve. What do you understand by the characteristic curve of turbine? Name the important types of characteristic curves. మూడు ఉన్నాయి కాబట్టి మూడు గురించి రాయండి. Define the term governing of turbine with the needs gauge, oil, pressure governor గురించి రాయండి. Give the range specific speeds of values of Kaplan, Francis and Pelton wheels. Draw the needs sketch of Pelton turbine and Francis turbine. Describe briefly the function and various components of Pelton turbine with needs sketch. What is a cavitation? How it can be avoided in a reaction turbine. ఏ టర్బైన్ కైనా సరే క్వశ్చన్ ఇలా ఇచ్చాడు అనుకోండి, రియాక్షన్ టర్బైన్ అన్నప్పుడు అదే రాయండి, పెల్టాన్ వీల్ అన్నప్పుడు అదే రాయండి, అదే ఏమైనా వేరేది వచ్చినా కూడా సేమ్ థింగ్ యూ హావ్ టు రైట్ ఇట్. రైట్? సో విత్ దిస్ విల్ వైండ్ అప్ ద సెషన్. With this we'll wind up the unit 5. So if you have any doubts, so that we can have a chat, have a talk or a chat. Anything to discuss, you can unlock your mic and you can talk to me. Governing of turbines కూడా నేను చెప్పాను. సర్జ్ ట్యాంక్ అంటే ఏంటి, రైట్? మీకు సిలబస్లో ఉంది కాబట్టి దాని గురించి కూడా మీకు నేను చూపిస్తాను. సర్జ్ ట్యాంక్. When the load of a generator decreases, the governor reduces the rate of the flow of water striking the runner to the main constant speed of the runner, right? So the surge tanks are employed in case of high head and medium head hydro power plants. Surge tanks eక్కడ యూస్ చేస్తున్నాం? These are employed in case of high head and medium head hydropower plants where the penstock is very long and 4 bays are suitable for the medium and low hydropower power plants, right? So surge tank gurinchi iస్తే ఇది రాయండి. Figure is like this, surge tank figure. Yeah, some technical issue. So this is a surge tank figure and governing of turbines గురించి ఒకసారి చేద్దాం. So the governing, see the governing of a Kaplan tube turbine is done by the means of oil pressure governor. So the following parts are oil sump, gear pump, the servometer, control valve, centrifugal valve, pipes and spear rod. So దీని ఆపరేషన్ గురించి ఇక్కడ డీటెయిల్ గా ఉంది. రన్నింగ్ నోట్స్ లో కూడా రాసుకున్నారు. ఒకసారి ఆపరేషన్ ఒకసారి చదవండి. ఇట్ విల్ బి ఈజీలీ understandable, right? So this is a figure of this governor of the Pelton turbine, right? See here how the oil is taken from the oil sump and it is flowing through this piston, cylinder and piston through the nozzle. This is spear anamata, right? The spear is moving to and fro. Ikkada spear vachesi to and fro move avutundi. Thereby మనకి nozzle లో వాటర్ ఫ్లష్ అవుతుంది కాబట్టి ఇది ముందుకి వెనక్కి వచ్చినప్పుడు you are having some sort of pressure difference in this oil, right? In this water. Then you are having two types of cylinder, piston cylinder valve ikkada undi, ikkada vachesi other piston cylinder valve. These are moved by using the servo motor mechanism. So upside of this pumps you are having a governor which is connected to the turbine main shaft. So these are the fly balls for the balancing of